In this video, we're going to go over Unit 2 review for the test on one-dimensional motion. On the front page, we're going to talk about the motion graphs, more specifically the position time graphs, and how you're supposed to describe the velocity and acceleration for each. If you're looking at a position time graph and you see a line representing the motion of the object, acceleration is going to be zero no matter what. Whether it's a horizontal line in this direction or it's a positive slope or a negative slope, the acceleration is always zero. The velocity is going to depend on the line itself. Is it getting further away from the source or is it getting closer? Look at the slope here. From left to right, so as time goes on, this graph goes up. Therefore, my velocity is going to be positive. And we know the velocity is constant, that's why the acceleration is zero. Number two, the velocity and acceleration of this graph. We notice that on a position time graph such as this, there's no linear portion of the graph. So therefore, we know for a fact that acceleration is not going to be zero. It's a non-zero acceleration. The question is it positive or is it negative? Let's answer that after we do velocity. Velocity, again, this object is getting further away. Velocity is going to be positive. A common misconception is that students want to believe that whatever velocity is positive, the acceleration has to be the same exact sign. Like, so if this is positive, they automatically assume the acceleration is positive as well. That is actually not true at all, and it can get you into some incorrect answers when you're trying to answer certain questions. Look at the actual curve. Is it getting steeper as time goes on? Because we know that a steeper slope represents a faster speed. So if you look here, I'll just choose a tangent line to the curve. Right here, that's my slope at time, 1, we'll call it. Let's fast forward to time, let's just assume it's 3. If I draw this tangent line, look at how much steeper this line is to this line. If your curve gets more vertical, that means it's speeding up. And objects that are speeding up, the acceleration is positive. Likewise, if my object was slowing down, my acceleration would be negative. Number 3, velocity and acceleration. Velocity, we notice that the object is getting closer to the source. It's decreasing as time goes on in this direction, so we know that's negative. By the mere fact that it's a position time graph and we see a line, we know the acceleration is 0 automatically. There's no change in velocity whatsoever. It is constant throughout the entire graph. Number 4, describe the velocity and acceleration. Velocity is going to be negative again. It's getting closer to the source. Let's check the acceleration. Is it speeding up or slowing down? This graph here, again, if you look towards the end, it's getting more steep. So we draw a tangent line right there, compare it to a tangent line from the beginning. It should be pretty obvious that this line here is steeper than this line here. So while this is traveling at some speed here, it's much slower than it is the speed right at this point here. So my acceleration, since I'm speeding up, is positive. So if you're looking at a position time graph, whenever you see a line, acceleration is automatically 0. If you see a curve, acceleration is going to be some non-zero, positive or negative, depending on if the object is speeding up or slowing down. 5, 6, and 7 change it up in that they use velocity time graphs instead of position time graphs. We already talked about the rules for position time graphs. Let's talk about velocity time graphs. Having a line on a velocity time graph does not necessarily mean that the acceleration is 0, like the other type of graph. So here, this graph here, we have velocity, positive to negative, 0 in the middle, versus time. First of all, let's describe the velocity. This should be somewhat easy. It's positive because it's above 0 in the positive direction. All right, so this y value here, we don't know what it is, we just know that it is positive. So we know velocity is positive. Let's check the acceleration. Is the velocity changing? Ask yourself that question. So is the velocity getting larger, smaller, or is it staying the same rate? Because this line is horizontal and not moving up or down, velocity isn't changing. So velocity isn't changing. And because of that, the acceleration is going to be 0. Because the line is not going up or down, my acceleration is 0. Number 6, another velocity time graph, but in this case, it's no longer a horizontal line representing our object. Velocity. By the end of it, we have increasing positive velocity. Our acceleration. Now, on the older graphs, we just talked about the distance time graph. When you see a line like this, you would automatically think the acceleration is 0 because I see a line. You'd be wrong to say that here because the velocity is changing. As you move up or to the right in time, my velocity is getting larger and larger, which means a change in velocity. So because I have a change in velocity, I know for a fact my acceleration is not equal to 0. Okay. Now, is the velocity increasing or the decreasing? From the graph, we can tell that it's increasing. So I know my acceleration is positive. It is speeding up. Number 7, we got somewhat of a piecewise graph here. 3 separate sections, A, B, and C. They represent different types of part of the motion of the object. A says describe the motion of object in interval A. This is a velocity time graph. Do not forget that. Part A, we have a constant velocity. Just because it's a horizontal line does not mean there's no motion at all. That would be true for a position time graph, but keep in mind we have velocity here. So describe the motion of the object in interval A. We have a positive constant velocity. And when you write down the word constant in front of velocity, you're telling people acceleration is 0. Part B, describe the motion of the object in interval B. If you look here, it's another line, but notice that the velocity is going from high to low. So we have a change in velocity here. So change in velocity. It's the very definition of acceleration. So describe the motion of the object in interval B. The acceleration is, you got to decide if it's positive or negative. If your object is going from a high velocity to a low velocity, that means it is slowing down. Your acceleration is negative. Now your velocity is still positive because it ends right here above 0, so we're still moving in a positive direction, we're just slowing down. So at no point did the object turn around, it just slowed, going from really fast to really slow. Part C, that interval, again, positive constant velocity. And that constant word, you're telling people acceleration is 0. Some people might want to say, I have a bunch of horizontal lines here, so this object stopped, it goes backwards, and it stopped again. That would be true for a position time graph, but be careful when you're looking at these graphs. Always check to see what the y variable is, if it's velocity or position, because it has different rules for each. It is only if you're looking for an object with no movement on a velocity time graph, you'd be right here on this 0 line. Because when your object, the line gets down to 0, that means there's 0 velocity, which means no movement at all. Okay, move on to some equation examples, starting with number 8. So before, we've taken assessments and done practice with every single type of problem segmented and put off into its own little group. On a test, though, everything's going to be mixed up. So you're going to have to go through and label the variables with the correct letters, and then you have to choose the correct equations. So for number 8, we have a person runs 100 meters east in 20 seconds. What is their average velocity? So we have velocity, we have distance, and we have time. I know for a fact we're using this equation. So that means we have to have 2 of these and finding the third. If they're asking for velocity, I know that I don't have that. Distance is given, 100 meters. Time, 20 seconds. Usually you would check to see if your units match up, but in this case, if you're doing a rate, you don't have to because you're dividing them anyways. If it said to give the velocity in miles per hour, you would simply just convert it afterwards. So velocity is going to be equal to 100 divided by 20, and you'll get 5 meters per second. Number 9. If an ice skater glides across ice at a speed of 8 meters per second over a distance of 12 meters, then how many seconds did the skater glide? So a skater glides across the ice at a speed of 8 meters per second over a distance of 12 meters. How many seconds did the skater glide? So we have a speed or velocity. We have a distance. And how many seconds is time? We don't know what that is. So plug in your values. We're going to have 8 equals 12 over t. Solving for t, you can multiply both sides by t and then divide by 8, or we can use the cross multiply method where you get 8t equals 12. Then you divide by that number in front of t. You get t equals 1.5 seconds. Okay. 10. A race car travels around a 2,000 meter track in 40 seconds. What was the average velocity? So average velocity we're looking for. The time is 40 seconds. The distance is 2,000 meters. So you're going to have V equals 2,000 divided by 40. That'll get you 50 meters per second. Now, you'll notice that it doesn't say velocity in a certain units. Whenever it doesn't give you the units it wants it in, just leave it as is, whatever is given to you. Okay. Number 11. A lady rides her bike 2,600 meters in 8 minutes. She then increases her speed and rides another 1,600 meters in 4.5 minutes. She takes a break and stops for 2 minutes. She then rides her bike another 3,000 meters in 12 minutes. A. How long did she ride her bike? Sorry. How long did her bike ride take? So that's total time. So you're simply going to add all the times together. So 8 minutes plus 4.5 minutes plus 12 minutes plus 2 minutes. You might be thinking to yourself, why should I count the break if she's not moving? If you're just doing average velocity from time 1 to time 2, whatever it is, you're counting in the stops in there. So with that total time, you get 26.5 minutes. How far did she ride? Take all your distances, 2,600, 1,600, plus 3,000, get 7,200 meters. So you'll notice we have 3 distances and 4 times. If you're adding more time than there are distances, that means your average velocity is going to decrease over time because you've stopped for that amount of time. What was her average speed? You take your distance traveled, which is 7,200, divided by the time, 26.5 minutes, and you're going to get 271.70 miles per minute. So it doesn't tell you to do it in hours, so just leave it like that. If it did ask you to convert it, you simply just convert the minutes into hours, and you have miles per hour. Number 12. An airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it's finally lifted off the ground. Determine the distance traveled before takeoff. So, determine the distance traveled. That's your question mark. Your acceleration is given to you, 3.20 meters per second squared. And time is 32.8 seconds. There's one bit of information that's not given to you, but you have to infer it. If an airplane is accelerating down a runway, at some point it had to start doing that, and it started doing that at a velocity of 0 meters per second. So that wasn't stated in the problem, but you have to be able to infer that. So the equation we're going to use that has all these variables, it's going to be d equals vi times t plus 1/2 a t squared. I'm noticing people are forgetting the square on the t. Please do not do that. Also understand that the square only goes to the time and not to the acceleration or the 1/2. So this is going to be d equals 0 times 32.8 plus 1/2 times 3.20 times 32.8 squared. And then when you calculate that, we get 1,721.34, and the units here are meters, which makes sense because this cancels out to 0. This is meters per second squared. This is going to be seconds squared. So the second squared and the second squared cancels out, and you're left with just meters. And that is your total distance. 13. A car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. So we're looking for the acceleration. We don't know what it is. We do know the time, 5.21 seconds. We do know the distance, 110 meters. And velocity initial is 0. Again, that number is not stated, but a car starting from rest means that it has an initial velocity of 0. So reuse the same exact equation. You're going to have 0 times 5.21 plus 1/2 times a times t squared, so 5.21 squared. And I've mistakenly wrote d here. This should be 110 because that's your distance. All right, so this is going to be 0, so that you don't have to write that anymore. You're going to have 110 equals 1/2 times 5.21 squared. When you multiply these two terms together, or these two numbers, you're going to get 13.57. A. One-step equation, divide both sides by 13.57. Your acceleration is going to be 8.11 meters per second squared. Your acceleration units are always distance per unit of time squared, because essentially what this means is your acceleration, 8.11 meters per second squared. Every 1 second, your speed or velocity increases by 8.11 meters per second. Moving on. Number 14. DJ Jazzy Jeff is riding the giant drop at the amusement park. If DJ Jazzy free falls for 2.6 seconds, what will his final velocity be and how far will he fall? So, he free falls for 2.6 seconds. We know the time. We know velocity initial because if he's being dropped, we know that you drop something at a 0 speed. Your acceleration, 9.8 meters per second squared. We know it's positive because when you drop something down, gravity speeds it up. So my acceleration being positive because my object is speeding up. And we want to know his final velocity first. And then we want to know how far he'll fall second. So we're going to find this first and this second. All right, so first one. Use the equation A equals VF minus VI over T. So VF minus 0 all over 2.6. And when you solve that, you get velocity final of 25.48 meters per second. That's the answer to the first part. The second part is looking for the distance. So that's the equation D equals initial velocity times time plus 1/2 times A, so 9.8, and then 2.6 squared. And when you calculate that, it's going to be 33.124 meters. Now, expect to see a problem like this where I don't ask you for the first thing, so it might just say this. It might just say, if he free falls for 2.6 seconds, how far will he fall? And you'll have to do, one or the other. Okay, or you might need to find this one to find the second piece. You just have to know your equations well enough to make that path for yourself. 15. Rocket-powered sleds are used to test the human response to acceleration. If a rocket-powered sled is accelerated to a speed of 444 meters per second in 1.8 seconds, then what is the acceleration and what is the distance with which the sled travels? So first, variables, 1.8 seconds. My velocity final is 444 meters per second. I don't know acceleration. I don't know the distance. And the velocity initial, I can assume, is 0. So, first, to find the acceleration, because acceleration exists in all the equations, you're going to use this equation. So that's going to be 444 minus 0 over 1.8. And your acceleration is 246.67 meters per second squared. So that's the answer to the first question. Asking what the distance is, then after that, you're going to have d equals 0 times 1.8 plus 1/2 times 246.67 times 1.8 squared. And your distance will be 399.61 meters. Keep track of units with this one, and then make sure that you're using the correct equations and plugging numbers in the correct spot. Number 16, a bike accelerates uniformly from rest to a speed of 7.10 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. Looking for acceleration, they give me a distance, they give me velocity initial, they give me velocity final, and they're asking for acceleration. Okay, so we're going to use the equation Vf squared equals Vi squared plus 2AD. Velocity final squared, 7.10 squared. Velocity initial is 0 plus 2 times A times D, D being 35.4. So we're going to have 50.41 equals 70.8A. Remember, 70.8 comes from 2 times 35.4. Divide both sides by 70.8. Your acceleration is going to be 0.712 meters per second squared. Now, I've seen students before, they mix up velocity initial and the velocity final. They swap them. What will happen there is that your acceleration will become negative. And you might think it's not a big deal, but on a multiple choice test, you're going to have both probably the positive and negative numbers of 0.712, and you'll have to choose the correct one. And if you chose velocity final and initial incorrectly, you'll get that incorrect. 17. An engineer is designing the runway for an airport. Of the planes which will use the airport, the lowest acceleration rate is likely to be 3 meters per second squared. The takeoff speed for this plane will be 65 meters per second. Assuming this minimum acceleration, what is the minimum allowed length for the runway? So the length would be your distance, is what we're looking for. Acceleration is given to us, 3 meters per second squared. Velocity final will be 65 meters per second. Velocity initial, we know that the plane starts at 0, and we're looking for distance. So we're going to use that equation, Vf squared equals Vi squared plus 2AD. So 2 times 3 times D. So that's going to be 4,225 equals 6D. That's 2 times 3 times D. Divide both sides by 6. Your distance will be 704.17 meters for your runway. 18. A baseball is popped straight up into the air and has a hang time of 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. Hint, the time to rise to the peak is 1/2 the total hang time. So, it's popped straight up into the air and has a hang time of 6.25 seconds. That means time up, time down are the same. You're going to take that time and cut it in half. So your actual time will be 3.125 seconds. And since it's going up, your acceleration is negative 9.8 meters per second squared because the object is slowing down due to gravity. Velocity final at its peak, we know that's 0 meters per second. When something is thrown up and starts coming back down, the point at which it stops going up and starts coming back down, that exact moment it ceases to have velocity, it's 0. So first, we're looking for the height. And we might need something in between there, because if we are looking for distance, have time and acceleration and final velocity, and we don't have the initial velocity, it's going to be hard for us to find it. So first, we're going to find initial velocity. Second, we're going to find distance. This is one of those problems where I don't tell you the in-between step, and you have to figure that out on your own. So keep in mind this problem. So first, we're going to use acceleration equals Vf minus Vi all over t. So negative 9.8 equals 0 minus velocity initial all over 3.125. My velocity initial, after you solve for it, 30.63 meters per second. We're going to use that to find our distance. It's going to be d equals 30.63 times the time, 3.125, plus 1/2 times negative 9.8 times 3.125 squared. Let me zoom in on that. And when you solve it, 47.87 meters. That would be your height. Okay. Last problem on the review. Zoom out a little bit. The observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. So we need to find the time required. We know the distance. Velocity final, I don't know. Velocity initial, I know is 0. And I know acceleration is 9.8 meters per second. So, if we're going to use, if we're going to find time, and we're given the distance, velocity initial, and the acceleration, with that equation, Vf squared equals Vi squared plus 2AD. There's no time here, but I can find the final velocity and then use that to find my time afterwards. So plug in your known values. So we're going to have 0 squared plus 2 times 9.8 times 370. And when you square root it, when you're done, velocity final should be 85.16 after you get done with all the evaluating and square rooting. After that, let's zoom in. We're going to use that velocity final in the basic acceleration equation. So 9.8 equals 85.16 minus 0 all over time. And when you solve for time, you get 8.69 seconds. Okay. So some problems require you to use multiple steps, solve for in-between variables. You have to be prepared for that. Know when you're reading when certain variables are implied. For example, something's from rest. I'm dropping something. Those velocities will be 0. If I throw something up and at its max height, it's going 0 meters per second or whatever unit of velocity you choose. You have to know those implications because they're not going to be stated for you in the problems. Make sure that you're marking your variables, and then you're choosing the correct equation, and then using the algebra skills you've been taught in the past to solve for those missing variables. Just to recap, position time graphs. When you have position time, linear graphs will imply that the acceleration is 0. A nonlinear graph will imply that the acceleration is non-zero, either positive or negative. It's speeding up or slowing down. It's speeding up if the curve is getting more vertical. If it's getting more horizontal, so if the curve looks more like a flattening out, that means the acceleration is actually negative. Velocity time graphs have different rules because you're measuring something different. So a line that's horizontal does not mean that the object's not moving on a velocity time graph like it would on a position time graph. In this case, it is a constant velocity. Acceleration will be 0. This example here, the line moving upwards, that's a changing velocity because my y direction is velocity. Even though it's a line, acceleration would be positive there. So just make sure you know what graph you're looking at, and then make sure you understand the definitions of velocity and acceleration respectively.